Chapter 5 Surface Chemistry. Surface chemistry deals with phenomena that occur at surfaces or interfaces. The interface or surface is represented by separating the bulk phases by a hyphen or a slash. For example, the interface between a solid and a gas may be represented by solid hyphen gas or solid slash gas. Due to complete miscibility, there is no interface between the gases. The bulk phases that we come across in surface chemistry may be pure compounds or solutions. The interface is normally a few molecules thick, but its area depends on the size of the particles of bulk phases. Many important phenomena noticeable amongst these being corrosion, electrode processes, heterogeneous catalysis, dissolution, and crystallization occur at interfaces. The subject of surface chemistry finds many applications in industry, analytical work, and daily life situations. To accomplish surface studies meticulously, it becomes imperative to have a really clean surface under very high vacuum of the order of 10 raised to minus 8 to 10 raised to minus 9 Pascal. It is now possible to obtain ultra clean surface of the metals. Solid materials with such clean surfaces need to be stored in vacuum, otherwise, these will be covered by molecules of major components of air, namely dioxygen and dinitrogen. In this unit, you will be studying some important features of surface chemistry such as adsorption, catalysis, and colloids, including emulsions and gels. Adsorption. There are several examples which reveal that the surface of a solid has the tendency to attract and retain the molecules of the phase with which it comes into contact. These molecules remain only at the surface and do not go deeper into the bulk. The accumulation of molecular species at the surface rather than in the bulk of a solid or liquid is termed as adsorption. The molecular species or substance which concentrates or accumulates at the surface is termed adsorbate, and the material on the surface of which adsorption takes place is called adsorbent. Adsorption is essentially a surface phenomenon. Solids, particularly in finely divided state, have large surface area and therefore charcoal, silica gel, alumina gel, clay, colloids, metal in finely divided state, etc. act as good adsorbents. Adsorption in action. First, if a gas like O2, H2, carbon monoxide, chlorine gas, ammonia, or sulfur dioxide is taken in a closed vessel containing powdered charcoal, it is observed that the pressure of the gas in the enclosed vessel decreases. The gas molecules concentrate at the surface of the charcoal, that is, gases are adsorbed at the surface. Second, in a solution of an organic dye, say methylene blue, when animal charcoal is added and the solution is well shaken, it is observed that the filtrate turns colorless. The molecules of the dye thus accumulate on the surface of the charcoal, that is, are adsorbed. Third, aqueous solution of raw sugar when passed over beds of animal charcoal becomes colorless as the coloring substances are adsorbed by the charcoal. Fourth, the air becomes dry in the presence of silica gel because the water molecules get adsorbed on the surface of the gel. It is clear from the above example that solid surfaces can hold the gas or liquid molecules by virtue of adsorption. The process of removing an adsorbed substance from a surface on which it is adsorbed is called desorption. Distinction between adsorption and absorption. In adsorption, the substance is concentrated only at the surface and does not penetrate through the surface to the bulk of the adsorbent, while in absorption, the substance is uniformly distributed throughout the bulk of the solid. For example, when a chalk stick is dipped in ink, the surface retains the color of the ink due to adsorption of the colored molecules, while the solvent of the ink goes deeper into the stick due to absorption. On breaking the chalk stick, it is found to be white from inside. A distinction can be made between absorption and adsorption by taking an example of water vapor. Water vapors are absorbed by anhydrous calcium chloride but adsorbed by silica gel. In other words, in adsorption, the concentration of the adsorbate increases only at the surface of the adsorbent, while in absorption, the concentration is uniform throughout the bulk of the solid. Both adsorption and absorption can take place simultaneously also. The term sorption is used to describe both the process. Mechanism of adsorption. Adsorption arises due to the fact that the surface particle of the adsorbent are not in the same environment as the particles inside the bulk. Inside the adsorbent, all the forces acting between the particles are mutually balanced. But on the surface, the particles are not surrounded by atoms or molecules of their kind on all sides, and hence they possess unbalanced or residual attractive forces. These forces of the adsorbent are responsible for attracting the adsorbate particles on its surface. The extent of adsorption increases with the increase of surface area per unit mass of the adsorbent at a given temperature and pressure. Another important factor featuring adsorption is the heat of adsorption. During adsorption, there is always a decrease in residual forces of the surface. That is, there is decrease in surface energy which appears as heat. Adsorption, therefore, is invariably an exothermic process. In other words, delta H of adsorption is always negative. When a gas is adsorbed, the freedom of movement of its molecules become restricted. This amounts to decrease in the entropy of the gas after adsorption. That is, delta S is negative. Adsorption is thus accompanied by decrease in enthalpy as well as decrease in entropy of the system. For a process to be spontaneous, the thermodynamic requirement is that at constant temperature and pressure, delta G must be negative. That is, there is decrease in Gibbs energy. On the basis of equation, delta G is equal to delta H minus T delta S. Delta G can be negative if delta H has sufficiently high negative values as minus T delta S is positive. Thus, in an adsorption process which is spontaneous, a combination of these two factors make delta G negative. As the adsorption proceeds, delta H becomes less and less negative. Ultimately, delta H equal to T delta S and delta G becomes 0. At this state, equilibrium is attained. Types of adsorption. There are mainly two types of adsorption of gases on solids. If accumulation of gas on the surface of solid occurs on account of weak van der Waals forces, the adsorption is termed as physical adsorption or physisorption. When the gas molecules or atoms are held to the solid surface by chemical bonds, the adsorption is termed chemical adsorption or chemisorption. The chemical bonds may be covalent or ionic in nature. Chemisorption involves a high energy of activation and is therefore often referred to as activated adsorption. Sometimes these two processes occur simultaneously and it is not easy to ascertain the type of adsorption. A physical adsorption at low temperature may pass into chemisorption as the temperature is increased. For example, dihydrogen is first adsorbed on nickel by van der Waals forces. Molecules of hydrogen then dissociate to form hydrogen atoms, which are held on the surface by chemisorption. Some of the important characteristics of both types of adsorption are described below. Characteristic of physisorption. First, lack of specificity. A given surface of an adsorbent does not show any preference for a particular gas as the van der Waals forces are universal. Second, nature of adsorbent. The amount of gas adsorbed by a solid depends on the nature of the gas. In general, easily liquefiable gases, that is, with higher critical temperatures, are readily adsorbed as van der Waals forces are stronger near the critical temperatures. Thus, 1 gram of activated charcoal adsorbs more sulfur dioxide. Critical temperature 630 Kelvin, then methane, critical temperature 190 Kelvin, which is still more than 4.5 ml of dihydrogen, critical temperature 33 Kelvin. Third, reversible nature. Physical adsorption of a gas by a solid is generally reversible. Thus, solid plus gas may give gas/solid plus heat. More of gas is adsorbed when pressure is increased as the volume of the gas decreases. Le Chatelier's principle. And the gas can be removed by decreasing pressure. Since the adsorption process is exothermic, the physical adsorption occurs readily at low temperature and decreases with increasing temperature. Le Chatelier's principle. Fourth, surface area of adsorbent. The extent of adsorption increases with the increase of the surface area of the adsorbent. Thus, finely divided metals and porous substances having large surface area are good adsorbents. Fifth, enthalpy of adsorption. No doubt, physical adsorption is an exothermic process, but its enthalpy of adsorption is quite low, 20 to 40 kilojoule per mole. This is because the attraction between gas molecules and solid surface is only due to weak van der Waals forces. Characteristic of chemisorption. First, high specificity. Chemisorption is highly specific and it will only occur if there is some possibility of chemical bonding between adsorbent and adsorbate. For example, oxygen is adsorbed on metals by virtue of oxide formation and hydrogen is adsorbed by transition metals due to hydride formation. Second, irreversibility. As chemisorption involves compound formation, it is usually irreversible in nature. Chemisorption is also an exothermic process, but the process is very slow at low temperatures on account of high energy of activation. Like most chemical changes, adsorption often increases with the rise of temperature. Physisorption of a gas adsorbed at low temperature may change into chemisorption at a higher temperature. Usually, high pressure is also favorable for chemisorption. Third, surface area. Like physical adsorption, chemisorption also increases with increase of surface area of the adsorbent. Fourth, enthalpy of adsorption. Enthalpy of chemisorption is high, 80 to 240 kilojoule per mole, as it involves chemical bond formation. Table 5.1, it shows comparison of physisorption and chemisorption. So for physisorption, it arises because of van der Waals forces. Chemisorption, it is caused by chemical bond formation. Physisorption is not specific in nature. Chemisorption is highly specific in nature. Physisorption is reversible in nature. Chemisorption is irreversible. Physisorption depends on the nature of the gas. More easily liquefiable gases are adsorbed readily. Chemisorption also depends on the nature of gas. Gases which can react with the adsorbent show chemisorption. Enthalpy of adsorption is low, that is 20 to 40 kilojoule per mole in physisorption, whereas enthalpy of adsorption is high, 80 to 240 kilojoule per mole in chemisorption. Low temperature is favorable for adsorption. It decreases with increase of temperature, whereas high temperature is favorable for adsorption. It increases with the increase of temperature. In physisorption, no appreciable activation energy is required. In chemisorption, high activation energy is sometimes needed. In physisorption, it depends on the surface area. It increases with an increase of surface area. Whereas in chemisorption, it also depends on the surface area. It also increases with an increase of the surface area. Last, physisorption results in multimolecular layers on adsorbent surface under high pressure. Whereas in chemisorption, it results in unimolecular layer. That's it. Adsorption isotherms. The variation in the amount of gas adsorbed by the adsorbent with pressure at constant temperature can be expressed by means of a curve termed as adsorption isotherm. Freundlich adsorption isotherm. Freundlich in 1909 gave an empirical relationship between the quantity of gas adsorbed by unit mass of solid adsorbent and pressure at a particular temperature. The relationship can be expressed by the following equation. X by m is equal to k dot p raised to 1 by n, where n is greater than 1. You can look on the screen for the equation to get a correct idea, okay? Where x is the mass of the gas adsorbed on mass m of the adsorbent at a pressure p. K and N are constant, which depend on the nature of the adsorbent and the gas at a particular temperature. The relationship is generally represented in the form of a curve where mass of the gas adsorbed per gram of the adsorbent is plotted against pressure. These curves indicate that at a fixed pressure there is decrease in physical adsorption with increase in temperature. These curves always seem to approach saturation at high pressure. Taking logarithm of equation 5.1, log x by m is equal to log k plus 1 by n log p. The validity of Freundlich isotherm can be verified by plotting log x by m on y-axis and log p on x-axis. If it comes to be a straight line, the Freundlich isotherm is valid, otherwise not. The slope of the straight line gives the value of 1 by n. The intercept on y-axis gives the value of log k. Freundlich isotherm explains the behavior of adsorption in an approximate manner. The factor 1 by n can have values between 0 and 1. Probable range 0.1 to 0.5. Thus, equation 5.2 holds good over a limited range of pressure. When 1 by n is equal to 0, x by m is equal to constant. The adsorption is independent of pressure. When 1 by n is equal to 1, x by m is equal to kp. That is, x by m is directly proportional to pressure p. The adsorption varies directly with pressure. Both the conditions are supported by experimental results. The experimental isotherms always seem to approach saturation at high pressure. This cannot be explained by Freundlich isotherm. Thus, it fails at high pressure. Adsorption from solution phase. Solids can adsorb solutes from solutions also. When a solution of acetic acid in water is shaken with charcoal, a part of the acid is adsorbed by the charcoal and the concentration of the acid decreases in the solution. Similarly, the litmus solution when shaken with charcoal becomes colorless. The precipitate of magnesium hydroxide attains blue color when precipitated in presence of magnesium reagent. The color is due to adsorption of magnesium. The following observations have been made in the case of adsorption from solution phase. First, the extent of adsorption decreases with an increase in temperature. Second, the extent of adsorption increases with an increase of surface area of the adsorbent. Third, the extent of adsorption depends on the concentration of the solute in the solution. Fourth, the extent of adsorption depends on the nature of the adsorbent and the adsorbate. The precise mechanism of adsorption from solution is not known. Freundlich's equation approximately describes the behavior of adsorption from solution with a difference that instead of pressure, concentration of the solution is taken into account. That is, x by m is equal to kc raised to 1 by n. C is the equilibrium concentration, that is when adsorption is complete. On taking logarithm of the above equation, we have log x upon m is equal to log k plus 1 by n log c. Plotting log x by m against log c, a straight line is obtained, which shows the validity of Freundlich isotherm. This can be tested experimentally by taking solutions of different concentration of acetic acid. Equal volume of solutions are added to equal amounts of charcoal in different flasks. The final concentration is determined in each flask after adsorption. The difference in the initial and final concentration give the value of x. Using the above equation, validity of Freundlich isotherm can be established. Applications of adsorption. The phenomenon of adsorption finds a number of applications. Important ones are listed here. First, production of high vacuum. The remaining traces of air can be adsorbed by charcoal from a vessel evacuated by a vacuum pump to give a very high vacuum. Second, gas mask. Gas mask, a device which consists of activated charcoal or mixture of adsorbents, is usually used for breathing in coal mines to adsorb poisonous gases. Third, control of humidity. Silica and aluminium gels are used as adsorbents for removing moisture and controlling humidity. Fourth, removal of coloring matter from solutions. Animal charcoal removes color of solutions by adsorbing colored impurities. Fifth, heterogeneous catalysis. Adsorption of reactants on the solid surface of the catalyst increases the rate of reaction. There are many gaseous reactions of industrial importance involving solid catalyst, manufacture of ammonia using iron as a catalyst, manufacture of H2SO4 by contact process, and use of finely divided nickel in the hydrogenation of oils are excellent examples of heterogeneous catalysis. Sixth, separation of inert gases. Due to the difference in degree of adsorption of gases by charcoal, a mixture of noble gases can be separated by adsorption on coconut charcoal at different temperatures. Seventh, in curing diseases, a number of drugs are used to kill germs by getting adsorbed on them. Eighth, froth flotation process. A low-grade sulfite ore is concentrated by separating it from silica and other earthy matter by this method using pine oil and frothing agent, as can see in Unit 6. Ninth, adsorption indicators. Surfaces of certain precipitates such as silver halides have the property of adsorbing some dyes like eosine, fluorescein, etc., and thereby producing a characteristic color at the end point. Chromatographic analysis. Chromatographic analysis based on the phenomenon of adsorption finds a number of applications in analytical and industrial field. Catalysis. Potassium chlorate, when heated strongly, decomposes slowly, giving dioxygen. The decomposition occur in the temperature range of 653 to 873 Kelvin. KClO3, when heated strongly, it will give KCl plus oxygen gas. However, when a little of magnesium dioxide is added, the decomposition takes place at a considerably lower temperature range, that is 473 to 633 Kelvin, and also at much accelerated rate. The added manganese dioxide remains unchanged with respect to its mass and composition. In a similar manner, the rates of a number of chemical reactions can be altered by the mere presence of foreign substances. The systematic study of the effect of various foreign substances on the rates of chemical reaction was first made by Berzelius in 1835. He suggested the term catalyst for such substances. सो इफ़ यू आर लिसनिंग टू माई ऑडियो तो अगर किसी को पता हो कि बर्जीलियस का ऑर्गेनिक केमिस्ट्री में क्या कॉन्ट्रीब्यूशन था तो जस्ट कमेंट डाउन इन द कमेंट सेक्शन. Substances which accelerate the rate of a chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalyst, and the phenomenon is known as catalysis. You have already studied about catalyst and its functioning in section 4.5. Promoters and poisons. Promoters are substances that enhance the activity of a catalyst, while poisons decrease the activity of a catalyst. For example, in Haber's process for manufacture of ammonia, molybdenum acts as a promoter for iron, which is used as catalyst. And N2 gas plus 3 hydrogen gas in the presence of molybdenum solid and iron solid gives ammonia. Homogeneous and heterogeneous catalysis. Catalysis can be broadly divided into two groups. Homogeneous catalysis, when the reactants, products and the catalyst are in the same phase, that is liquid or gas. The process is said to be homogeneous catalysis. The following are some of the examples of homogeneous catalysis. First, oxidation of sulfur dioxide into sulfur trioxide with dioxygen in presence of oxides of nitrogen as catalyst in the lead chamber process. Sulfur dioxide with oxygen in presence of NO gives SO3. The reactants sulfur dioxide and oxygen and the catalyst also, that is nitric oxide, all are in the same phase. Second, hydrolysis of methyl acetate is catalyzed by H plus ions furnished by hydrochloric acid. Both the reactants and the catalyst are in the same phase. मतलब ये जो methyl acetate है, water है, और जो catalyst यूज़ किया है H plus ions HCl के फॉर्म में, तो सारे क्या है, लिक्विड फेज में ही है. Third, hydrolysis of sugar is catalyzed by H plus ions furnished by sulfuric acid. So here you can see the reaction C12H22O11 in presence of water, it gives glucose plus fructose. Both the reactants and catalyst are in the same phase. Heterogeneous catalysis. The catalytic process in which the reactants and the catalyst are in different phases is known as heterogeneous catalysis. Some of the examples of heterogeneous catalysis are given below. First, oxidation of sulfur dioxide into sulfur trioxide in the presence of platinum, that is PT. The reactant is in gaseous state, that is sulfur dioxide, while the catalyst, that is platinum, is in solid state. Second, combination between dinitrogen and dihydrogen to form ammonia in the presence of finely divided iron in Haber's process. N2 gas plus 3 hydrogen gas in presence of iron gives ammonia. The reactants N2 और जो हाइड्रोजन है वो कौन से फेज में, गैशियस फेज में, लेकिन जो कैटलिस्ट है आयरन दैट इज इन सॉलिड स्टेट, सॉलिड फेज. ओके. थर्ड, ऑक्सीडेशन ऑफ अमोनिया into nitric oxide in the presence of platinum gauze in Oswald's process. अगेन अगर आप देखोगे तो अमोनिया और ऑक्सीजन जो यूज हुआ है रिएक्टेंट्स आर इन गैशियस फेज, वेरेज जो कैटलिस्ट यूज हुआ है वो सॉलिड फेज में, प्लैटिनम गॉज. फोर्थ, हाइड्रोजनेशन ऑफ वेजिटेबल ऑयल्स इन द प्रेजेंस ऑफ फाइनली डिवाइडेड निकल एज कैटलिस्ट. वेजिटेबल्स ऑयल लिक्विड में है, हाइड्रोजन गैस सॉलिड, हाइड्रोजन गैस में है, एंड जो निकल यूज हुआ है कैटलिस्ट है वो सॉलिड फेज में, और क्या दे देगा वो आपको, वेजिटेबल घी. ठीक है. सो वन ऑफ द रिएक्टेंट्स इज इन लिक्विड स्टेट, द अदर इज इन गैशियस स्टेट, व्हाइल द कैटलिस्ट इज इन द सॉलिड स्टेट. तो दिस वाज द एग्जांपल ऑफ हेटेरोजेनस कैटलिसिस. Adsorption theory of heterogeneous catalysis. This theory explains the mechanism of heterogeneous catalysis. The old theory known as adsorption theory of catalysis was that the reactants in the gaseous state or in solutions are adsorbed on the surface of the solid catalyst. The increase in the concentration of the reactants on the surface increases the rate of reaction. Adsorption being an exothermic process, the heat of adsorption is utilized in enhancing the rate of the reaction. The catalytic action can be explained in the terms of intermediate compound formation, the theory of which you have already studied in section 4.5.1. The modern adsorption theory is combination of intermediate compound formation theory and old adsorption theory. The catalytic activity is localized on the surface of the catalyst. The mechanism involves 5 steps. First, diffusion of the reactants to the surface of the catalyst. Second, adsorption of the reactant molecules on the surface of the catalyst. Third, occurrence of chemical reaction on the catalyst surface through formation of an intermediate. Fourth, desorption of reaction products from the catalyst surface and thereby making the surface available again for more reaction to occur. Fifth, diffusion of reaction products away from the catalyst surface. The surface of the catalyst, unlike the inner part of the bulk, has free valencies which provide the seat for chemical forces of attraction. When a gas comes in contact with such a surface, its molecules are held up there due to loose chemical combination. If different molecules are adsorbed side by side, they may react with each other, resulting in the formation of new molecules. Thus, formed molecules may evaporate, leaving the surface for the fresh reactant molecules. This theory explains why the catalyst remains unchanged in mass and chemical composition at the end of the reaction and is effective. And are effective even in small quantities. It, however, does not explain the action of catalytic promoters and catalytic poisons. Important features of solid catalyst. A. Activity. The activity of a catalyst depends upon the strength of chemisorption to a large extent. The reactants must get adsorbed reasonably strongly onto the catalyst to become active. However, they must not get adsorbed so strongly that they are immobilized and other reactants are left with no space on the catalyst surface for adsorption. It has been found that for hydrogenation reaction, the catalytic activity increases from group 5 to group 11. Metals with maximum activity being shown by group 7 to 9 elements of the periodic table. 2H2 gas plus O2 gas in presence of platinum will give you water. Second, selectivity. The selectivity of a catalyst is its ability to direct a reaction to yield a particular product selectively. When under the same reaction conditions, many products are possible. Selectivity of different catalysts for same reactants is different. For example, starting with H2 and carbon monoxide and using different catalysts, we get different products. See, in the first, when carbon monoxide and hydrogen is used in presence of nickel as a catalyst, the product obtained is methane gas and water. Second, again carbon monoxide and H2, that is hydrogen gas, is taken as the reactant in presence of copper, zinc oxide and chromium oxide as a catalyst. So, methyl alcohol is the product obtained. Carbon monoxide plus H2 gas, when in presence of copper, then formaldehyde is obtained. ठीक है. सो निकल यूज किया तो मेथेन मिला, कॉपर जिंक ऑक्साइड यूज किया तो अल्कोहल मिला एंड सिर्फ कॉपर यूज किया तो अल्डिहाइड मिल गया with the same reactants. Thus, it can be inferred that the action of catalyst is highly selective in nature. As a result of substance which act as a catalyst in one reaction may fail to catalyze another reaction. Shape selective catalysis by zeolites. The Catalytic reaction that depends upon the pore structure of the catalyst and the size of the reactant and product molecules is called shape selective catalysis. Zeolites are good shape selective catalysts because of their honeycomb like structures. They are microporous aluminosilicates with three-dimensional network of silicates in which some silicon atoms are replaced by aluminium atoms, giving aluminium oxygen silicon framework. The reactions taking place in zeolites depend upon the size and the shape of the reactant and product molecules as well as upon the pores and the cavities of zeolite. They are found in nature as well as synthesized for catalytic selectivity. Zeolites are being very widely used as catalyst in petrochemical industries for cracking of hydrocarbons and isomerization. An important zeolite catalyst used in petroleum industry is ZSM/5. It converts alcohols directly into gasoline, petrol, by dehydrating them to give a mixture of hydrocarbons. Enzyme catalysis. Enzymes are complex nitrogenous organic compounds which are produced by living plants and animals. They are actually protein molecules of high molecular mass and form colloidal solutions in water. They are very effective catalysts, catalyze numerous reactions, especially those connected with natural processes. Numerous reactions that occur in the bodies of animals and plants to maintain the life processes are catalyzed by enzymes. The enzymes are thus termed as biochemical catalyst and the phenomenon is known as biochemical catalysis. Many enzymes have been obtained in pure crystalline state from living cells. However, the first enzyme was synthesized in the laboratory in 1969. The following are some of the examples of enzyme catalyzed reaction. First, inversion of cane sugar. The invertase enzyme converts cane sugar into glucose and fructose. The C12H22O11 in aqueous medium plus H2O in the presence of invertase it will give glucose and fructose. तो ये वाले रिएक्शन तो आपके बायोमोलिक्यूल्स के चैप्टर में भी है, राइट? तो वहाँ से भी लिंक कर सकते हो. Second, conversion of glucose into ethyl alcohol. The zymase enzyme converts glucose into ethyl alcohol and carbon dioxide. तो इन्वर्टेस ने क्या किया? केन शुगर को ग्लूकोज और फ्रक्टोज बना दिया. जाइमेस ने क्या किया? ग्लूकोज को इथाइल अल्कोहल और कार्बन डाइऑक्साइड बना दिया. थर्ड, कन्वर्जन ऑफ स्टार्च इनटू माल्टोज. द डाइएस्टेस एंजाइम कन्वर्ट्स स्टार्च इनटू माल्टोज. तो स्टार्च थोड़ा सा पानी इन प्रेजेंस ऑफ डाइएस्टेस क्या बना देगा? माल्टोज. फोर्थ, कन्वर्जन ऑफ माल्टोज इनटू ग्लूकोज. तो कौन चाहिए? माल्टेस. The maltase enzyme converts maltose into glucose. Fifth, decomposition of urea into ammonia and carbon dioxide. The enzyme urease catalyzes this decomposition. तो यूरिया लिया, थोड़ा सा पानी लिया, तो क्या बन जाएगा? अमोनिया एंड कार्बन डाइऑक्साइड गैस विल बी रिलीज्ड. तो which was that enzyme? Urease. Sixth, in stomach, the pepsin enzyme converts proteins into peptides, while in intestine, the pancreatic trypsin converts proteins into amino acids by hydrolysis. Seventh, conversion of milk into curd. It is an enzymatic reaction brought about by lactobacilli enzyme present in curd. Table 5.2 gives the summary of some important enzymatic reaction. तो एंजाइम का नाम है इन्वर्टेज. किससे मिलता है? ईस्ट से मिलता है. रिएक्शन क्या है? सुक्रोज कन्वर्ट हो जाता है ग्लूकोज एंड फ्रक्टोज में. एंजाइम जो है जाइमेस है, कहाँ से मिला? ईस्ट से मिला. क्या करता है? ग्लूकोज को कन्वर्ट कर देता है इथाइल अल्कोहल एंड कार्बन डाइऑक्साइड में. एंजाइम का नाम है डाइएस्टेस. सोर्स है माल्ट. क्या करता है वो? स्टार्च को माल्टोस में कन्वर्ट कर देता है. माल्टेस एंजाइम का नाम है. कहाँ से मिला? ईस्ट से मिला. क्या करता है वो? माल्टोस को कन्वर्ट कर देता है ग्लूकोज में. एंजाइम यूरिएस जो है सोयाबीन से मिला है, वो क्या करता है, यूरिया को अमोनिया एंड कार्बन डाइऑक्साइड बना देता है। पेप्सिन कहाँ पर प्रेजेंट है, हमारे स्टमक में, और वो क्या करता है, प्रोटीन्स को कन्वर्ट कर देता है अमीनो एसिड्स में। ठीक है। कैरेक्टरिस्टिक्स ऑफ एंजाइम कैटालिसिस। Enzyme catalysis is unique in its efficiency and high degree of specificity. The following characteristics are exhibited by enzyme catalyst. First, most highly efficient. One molecule of an enzyme may transform 1 million molecules of the reactant per minute. Second, highly specific nature. Each enzyme is specific for a given reaction. That is, one catalyst cannot catalyze more than one reaction. For example, the enzyme urease catalyzes the hydrolysis of urea only. It does not catalyze hydrolysis of any other amide. Third, highly active under optimum temperature. The rate of an enzyme reaction becomes maximum at a definite temperature called the optimum temperature. On either side of the optimum temperature, the enzyme activity decreases. The optimum temperature range for enzymatic activity is 298 to 310 Kelvin. Human body temperatures being 310 Kelvin is suited for enzyme catalyzed reactions. Fourth, highly active under optimum pH. The rate of an enzyme catalyst reaction is maximum at a particular pH called optimum pH, which is between pH values 5 to 7. Fifth, increasing activity in presence of activators and coenzyme. The enzymatic activity is increased in the presence of certain substances known as coenzyme. It has been observed that when a small non-protein vitamin is present along with an enzyme, the catalytic activity is enhanced considerably. Activators are generally metal ions such as Na+, Mn2+, CO2+, Cu2+, etc. These metal ions, when weakly bonded to enzyme molecules, increase their catalytic activity. Amylase in presence of sodium chloride, that is Na plus ions, are catalytically very active. Sixth, influence of inhibitors and poisons. Like ordinary catalysts, enzymes are also inhibited or poisoned by presence of certain substances. The inhibitors or poisons interact with the active functional groups on the enzyme surface and often reduce or completely destroy the catalytic activity of the enzymes. The use of many drugs is related to their action as enzyme inhibitors in the body. Mechanism of enzyme catalysis. There are a number of cavities present on the surface of colloidal particles of the enzymes. These cavities are of characteristic shape and possesses active groups such as NH2, COOH, SH, OH, etc. These are actually the active centers on the surface of the enzyme particles. The molecules of the reactant substrate which have complementary shape fit into these cavities just like a key fit into a lock. On account of the presence of active groups, an activated complex is formed which then decomposes to yield the product. Thus, the enzyme catalyzed reactions may be considered to proceed in two steps. First, binding of enzyme to substrate to form an activated complex. मतलब enzyme plus substrate क्या दे देगा, enzyme substrate complex. Second, decomposition of the active complex to form product. तो यही एंजाइम सबस्ट्रेट कॉम्प्लेक्स टूटेगा और वो क्या दे देगा, एंजाइम को अलग कर देगा एंड प्रोडक्ट फॉर्मेशन कर देगा. कैटलिस्ट इन इंडस्ट्री. Some of the important technical catalytic processes are listed in table 5.3 to give an idea about the utility of catalyst in industries. तो आप देख सकते हो प्रोसेस, हेबर्स प्रोसेस फॉर मैन्युफैक्चर ऑफ अमोनिया. तो वहाँ पर क्या होता है, फाइनली डिवाइडेड आयरन, मोलिब्डेनम एज प्रमोटर, conditions 200 bar pressure and 723 to 773 Kelvin temperature. Nowadays, a mixture of iron oxide, potassium oxide and alumina is also used. फिर प्रोसेस ओसवाल्ड्स प्रोसेस में फॉर मैन्युफैक्चर ऑफ नाइट्रिक एसिड. तो नाइट्रिक एसिड कैसे बना सकते हो, दैट इज HNO3. ओसवाल्ड प्रोसेस के स्टेप्स है. अमोनिया लो, उसे नाइट्रिक ऑक्साइड बनाओ, नाइट्रिक ऑक्साइड लो, उसे नाइट्रोजन डाइऑक्साइड बनाओ, नाइट्रोजन डाइऑक्साइड लो, पानी से मिलाओ, ऑक्सीजन से मिलाओ और नाइट्रिक एसिड बन गया। कैटलिस्ट कौन सा यूज होता है? प्लैटिनाइज्ड एस्बेस्टोस। टेम्परेचर कितना लगता है? 573 केल्विन। थर्ड, कॉन्टैक्ट प्रोसेस फॉर मैन्युफैक्चर ऑफ सल्फ्यूरिक एसिड। तो सल्फ्यूरिक एसिड कैसे बनेगा? सल्फर डाइऑक्साइड लो, उससे क्या बनाओ? सल्फर ट्राइऑक्साइड। सल्फर ट्राइऑक्साइड लो और थोड़ा सा H2SO4 ऐड करो, उससे आपको क्या मिलेगा? ओलियम मिलेगा, H2H2O7। H2H2O7 मतलब ओलियम से पानी पास कर दो तो क्या मिल जाएगा? सल्फ्यूरिक एसिड। कैटलिस्ट क्या लग रहा है? प्लैटिनाइज्ड एस्बेस्टोस और वेनेडियम पेंटॉक्साइड V2O5। टेम्परेचर 673 केल्विन, 673 to 723 Kelvin. Colloids. We have learnt in Unit 2 that solutions are homogeneous systems. We also know that sand in water, when stirred, gives a suspension which slowly settles down with time. Between the two extremes of suspensions and solution, we come across a large group of systems called colloidal dispersions or simply colloids. A colloid is a heterogeneous system in which one substance is dispersed as very fine particles in another substance called dispersion medium. The essential difference between a solution and a colloid is that of the particle size. While in a solution, the constituent particles are ions of small molecules, in a colloid, the dispersed phase may consist of particles of a single macromolecule, such as protein or synthetic polymer, or an aggregate of many atoms, ions, or molecules. Colloidal particles are larger than simple molecules but small enough to remain suspended. Their range of diameters is between 1 and 1000 nanometer, that is 10 raised to minus 9 to 10 raised to minus 6 meter. Colloidal particles have an enormous surface area per unit mass as a result of their small size. Consider a cube with 1 centimeter side. It has a total surface area of 6 centimeters square. If it were divided equally into 10 raised to 12 cubes, the cubes would be the size of large colloidal particles and have a total surface area of 60,000 centimeters square or 6 meters square. This enormous surface area leads to some special properties of colloids to be discussed later in this unit. Classification of colloids. Colloids are classified on the basis of following criteria. First, physical state of dispersed phase and dispersion medium. Second, nature of interaction between dispersed phase and dispersion medium. Third, type of particles of the dispersed phase. Classification based on physical state of dispersed phase and dispersion medium. Depending upon whether the dispersed phase and the dispersion medium are solid, liquid, or gases, 8 types of colloidal systems are possible. A gas mixed with another gas forms a homogeneous mixture and hence is not a colloidal system. The examples of the various types of colloids along with their typical names are listed in table 5.4. Many familiar commercial products and natural objects are colloids. For example, whipped cream is a foam, which is a gas dispersed in a liquid. Firefighting foams used at emergency airplane landings are also colloidal systems. Most biological fluids are aqueous solid dispersed in water with a typical cell, proteins, and nucleic acid and are colloidal sized particles dispersed in an aqueous solution of ions and small molecules. So here you can see the table types of colloidal system. So you can just go through the table that what is dispersed phase, which is the dispersion medium, and what is the type of colloid that is formed. And there are certain examples also given. So just go through the table for a better understanding. Out of various type of colloids given in table 5.4, the most common are sols, solids in liquids, gels, liquids in solids, and emulsions, liquid in liquids. However, in the present unit, we shall take up discussion at the sols and emulsions only. Further, it may be mentioned that if the dispersion medium is water, the sol is called aquasol or hydrosol, and if the dispersion medium is alcohol, it is called alkosol, and so on. Classification based on nature of interaction between dispersed phase and dispersion medium. Depending upon the nature of interaction between the dispersed phase and the dispersion medium, colloidal sols are divided into two categories, namely lyophilic, solvent attracting, and lyophobic, solvent repelling. If water is the dispersion medium, the terms used are hydrophilic and hydrophobic. First, lyophilic colloids. The word lyophilic means liquid loving. Colloidal sols directly formed by mixing substances like gum, gelatin, starch, rubber, etc. with a suitable liquid, the dispersion medium, are called lyophilic sols. An important characteristic of these sols is that if the dispersion medium is separated from the dispersed phase, say by evaporation, the sol can be reconstituted by simply remixing with a dispersion medium. That is why these sols are also called reversible sols. Furthermore, these sols are quite stable and cannot be easily coagulated as discussed later. Lyophobic colloids. The word lyophobic means liquid hating. Substances like metals, disulfides, etc., when simply mixed with the dispersion medium, do not form the colloidal sol. The colloidal sols can be prepared only by special methods as discussed later. Such sols are called lyophobic sols. These sols are readily precipitated or coagulated on the addition of small amounts of electrolytes by heating or by shaking, and hence are not stable. Further, once precipitated, they do not give back the colloidal sol by simple addition of the dispersion medium. Hence, these sols are also called irreversible sols. Lyophobic sols need stabilizing agents for their preservation. Classification based on the type of particles of the dispersed phase: multimolecular, macromolecular, and associated colloids. Depending upon the type of particles of the dispersed phase, colloids are classified as multimolecular, macromolecular, and associated colloids. Multimolecular colloids. On dissolution, a large number of atoms or smaller molecules of a substance aggregate together to form species having size of the colloidal range 1 to 1000 nanometer. The species thus formed are called multimolecular colloids. For example, a gold sol may contain particles of various sizes having many atoms. Sulfur sol consists of particles consisting 1000 or more of the S8 sulfur molecules. Macromolecular colloids. Macromolecules in suitable solvents form solutions in which the size of the macromolecules may be in the colloidal range. Such systems are called macromolecular colloids. These colloids are quite stable and resemble true solutions in many respects. Examples of naturally occurring macromolecules are starch, cellulose, proteins, and enzymes. And those of man-made macromolecules are polythene, nylon, polystyrene, synthetic rubber, etc. Associated colloids. Micelles. There are some substances which at low concentration behave as normal strong electrolytes, but at high concentration exhibit colloidal behavior due to formation of aggregates. The aggregate particles thus formed are called micelles. These are also known as associated colloids. The formation of micelles takes place only above a particular temperature called craft temperature Tk and above a particular concentration called critical mycelial concentration CMC on dilution, these colloids revert back to individual ions. Surface active agents such as soap and synthetic detergents belong to this class. For soaps, the critically mycelial concentration is 10 raised to minus 4 to 10 raised to minus 3 moles per liter. These colloids have both lyophobic and lyophilic parts. Myceles may contain as many as 100 molecules or more. Mechanism of mycelial formation. Let us take the example of soap solution. Soap is sodium or potassium salt of higher fatty acid and may be represented as RCOO minus Na plus. Example, sodium stearate CH3 CH2 16 times COO minus Na plus, which is a major component of many bar soaps. When dissolved in water, it dissociates into RCOO minus and Na plus ions. The RCOO minus ions, however, consist of two parts. A long hydrocarbon chain R, also called a non-polar tail, which is hydrophobic, water repelling, and a polar group COO minus, also called polar ionic head, which is hydrophilic, water loving. The RCOO minus ions are therefore present on the surface with their COO minus groups in water, and the hydrocarbon chains are staying away from it and remain at the surface. But at critical mycelial concentration, the anions are pulled into the bulk of the solution and aggregate to form a spherical shape with their hydrocarbon chains pointing towards the center of the sphere, with COO minus part remaining outward on the surface of the sphere. An aggregate thus formed is known as ionic myceli. These myceli may contain as many as 100 such ions. Similarly, in case of detergents, example sodium lauryl sulfate CH3 CH2 11 times SO4 minus Na plus, the polar group is the SO4 minus along with the long hydrocarbon chain. Hence the mechanism of mycelial formation here also is same as that of soaps. Cleansing action of soaps. It has been mentioned earlier that a mycelium consists of a hydrophobic hydrocarbon like central core. The cleansing action of the soap is due to the fact that soap molecules form miceli around the oil droplet in such a way that hydrophobic part of the stearate ion is in the oil droplet and hydrophilic part projects out of the grease droplet like the bristles, as shown in figure 5.7. Since the polar groups can interact with water, the oil droplet surrounded by stearate ions is now pulled in water and removed from the dirty surface. Thus, soap helps in emulsification and washing away of oils and fats. The negatively charged sheath around the globules prevent them from coming together and form aggregates. A few important methods for preparation of colloids are as follows. 1. Chemical methods. Colloidal dispersion can be prepared by chemical reactions leading to formation of molecules by double decomposition, oxidation, reduction, or hydrolysis. These molecules then aggregate leading to formation of sols. So here you can see the reactions for double decomposition, for oxidation, for reduction, एंड फॉर हाइड्रोलिसिस. ठीक है, तो ये सब आप रिएक्शंस को देख सकते हो. SO2 के साथ किया है, देन FeCl3 के साथ दिया है, AuCl3 के साथ दिया हुआ है. ठीक है. B. Electrical disintegration or Braggs arc method. This process involves dispersion as well as condensation. Colloidal sols of metals such as gold, silver, platinum, etc. can be prepared by this method. In this method, electrical arc is struck between electrodes of metal immersed in the dispersion medium. The intense heat produced vaporizes the metal, which then condenses to form particles of colloidal size. Peptidization. Peptidization may be defined as the process of converting a precipitate into colloidal sol by shaking it with dispersion medium in the presence of a small amount of electrolyte. The electrolyte used for this purpose is called peptidizing agent. This method is applied generally to convert a freshly prepared precipitate into a colloidal sol. During peptidization, the precipitate absorbs one of the ions of the electrolyte on its surface. This causes the development of positive or negative charge on the precipitates, which ultimately break up into smaller particles of the size of a colloid. You will learn about the phenomenon of development of charge on solid particles and their dispersion in section 5.4.6 under heading Charge on Colloidal Particles. Purification of colloidal solutions. Colloidal solutions, when prepared, generally contain excessive amount of electrolytes and some other soluble impurities. While the presence of traces of electrolyte is essential for the stability of the colloidal solution, larger quantities coagulate it. It is therefore necessary to reduce the concentration of these soluble impurities to requisite minimum. The process used for reducing the amount of impurities to a requisite minimum is known as purification of colloidal solution. The purification of colloidal solution is carried out by the following method. First, dialysis. It is a process of removing a dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. Since particles, ions, or small molecule in a true solution can pass through animal membrane, bladder, or parchment paper or a cellophane sheet, but not the colloidal particles. The membrane can be used for dialysis. The apparatus used for this purpose is called dialyzer. A bag of suitable membrane containing the colloidal solution is suspended in a vessel through which fresh water is continuously flowing. The molecules and ions diffuse through membrane into the outer water and pure colloidal solution is left behind. Second, electrodialysis. Ordinarily, the process of dialysis is quite slow. It can be made faster by applying an electric field if the dissolved substance in the impure colloidal solution is only an electrolyte. The process is then named electrodialysis. The colloidal solution is placed in a bag of suitable membrane while pure water is taken outside. Electrodes are fitted in the compartment as shown in figure 5.10. The ions present in the colloidal solution migrate out to the oppositely charged electrodes. Third, ultrafiltration. Ultrafiltration is the process of separating the colloidal particles from the solvent and soluble solutes present in the colloidal solution by specifically prepared filters, which are permeable to all substances except the colloidal particles. Colloidal particles can pass through ordinary filter paper because the pores are too large. However, the pores of filter paper can be reduced in size by impregnating with colloidine solution to stop the flow of colloidal particles. The usual colloidine is a 4% solution of nitrocellulose in a mixture of alcohol and ether. An ultrafilter paper may be prepared by soaking the filter paper in a colloidine solution, hardening by formaldehyde, and then finally drying it. Thus, by using ultrafilter paper, the colloidal particles are separated from rest of the materials. Ultrafiltration is a slow process. To speed up the process, pressure or suction is applied. The colloidal particles left on ultrafilter paper and are then stirred with fresh dispersion medium solvent to get a pure colloidal solution. Properties of colloidal solution. Various properties exhibited by colloidal solutions are described below. First, colligative properties. Colloidal particles being bigger aggregates, the number of the particles in a colloidal solution is comparatively small as compared to a true solution. Hence, the values of colligative properties, osmotic pressure, lowering in vapor pressure, depression in freezing point, and elevation in boiling point are of small order as compared to values shown by true solution at same concentration. Second, Tyndall effect. If a homogeneous solution placed in dark is observed in the direction of light, it appears clear, and if it is observed from a direction at right angles to the direction of light beam, it appears perfectly dark. Colloidal solutions viewed in the same way may also appear reasonably clear or translucent by transmitted light, but they show a mild to strong opalescence when viewed at right angles to the passage of light. That is, the path of the beam is illuminated by a bluish light. This effect was first observed by Faraday and later studied in detail by Tyndall and is termed as Tyndall effect. The bright cone of the light is called Tyndall cone. The Tyndall effect is due to the fact that colloidal particles scatter light in all directions in space. This scattering of light illuminates the path of the beam in colloidal dispersion. Tyndall effect can be observed during the projection of a picture in the cinema hall. Due to scattering of light by dust and smoke particles present there, Tyndall effect is observed only when following two conditions are satisfied. First, the diameter of the dispersed particle is not much smaller than the wavelength of the light used. And second, the refractive indices of the dispersed phase and the dispersion medium differ greatly in magnitude. Tyndall effect is used to distinguish between a colloidal and true solution. Sigmondi in 1903 used Tyndall effect to set up an apparatus known as ultra microscope. An intense beam of light is focused on the colloidal solution contained in a glass vessel. The focus of the light is then observed with a microscope at right angles to the beam. Individual colloidal particles appear as bright stars against a dark background. Ultramicroscope does not render the actual colloidal particles visible but only observe the light scattered by them. Thus, ultramicroscope does not provide any information about the size and shape of the colloidal particles. Third, color. The color of the colloidal solution depends on the wavelength of light scattered by the dispersed particles. The wavelength of light further depends on the size and nature of the particles. The color of colloidal solution also changes with the manner in which the observer receives the light. For example, a mixture of milk and water appears blue when viewed by the reflected light and red when viewed by transmitted light. Finest gold sol is red in color. As the size of the particle increases, it appears blue. Then blue and finally golden. Brownian movement. When colloidal solutions are viewed under a powerful ultramicroscope, the colloidal particles appear to be in a state of continuous zigzag motion all over the field of view. This motion was first observed by British botanist Robert Brown and is known as Brownian movement. This motion is independent of the nature of the colloid but depends on the size of the particles and viscosity of the solution. Smaller the size and lesser the viscosity, faster is the motion. The Brownian movement has been explained to be due to the unbalanced bombardment of the particles by molecules of dispersion medium. The Brownian movement has a stirring effect which does not permit the particles to settle and thus is responsible for the stability of sols. Fifth, charge on colloidal particles. Colloidal particles always carry an electric charge. The nature of this charge is same on all the particles in a given colloidal solution and may be either positive or negative. A list of common sols with the nature of charge on their particles is given below. So here you can see positively charged sols, that is hydrated metallic oxides, basic dyestuffs, methylene blue, hemoglobin oxides. Whereas negatively charged sols are metals, direct metals, hydrated metal वगैरह कुछ नहीं. Metals, copper, silver, metallic sulfides, acidic dyestuff, Congo red sols, example, sol of starch, gum, gelatin, clay, charcoal, etc. The presence of equal and similar charges on colloidal particle is largely responsible in providing stability to the colloidal solution because the repulsive forces between charged particles having same charge prevent them from coalescing or aggregating when they come closer to one another. The charge on the soul particles is due to one or more reasons. That is, due to electron capture by soul particles during electrodispersion of metals due to preferential adsorption of ions from solution and or due to formation of electrical double layer. Development of charge on soul particles by preferential adsorption of ions is described below. The soul particles acquire positive or negative charge by preferential adsorption of positive or negative ions. When two or more ions are present in the dispersion medium, preferential adsorption of the ion common to the colloidal particle usually takes place. This can be explained by taking the following examples. A. When highly diluted solution of silver nitrate is added to highly diluted potassium iodide solution, the precipitated silver iodide adsorbs iodide ions from the dispersion medium and negatively charged colloidal soles results. However, when potassium iodide solution is added to HNO3 solution, positively charged sole results due to adsorption of Ag plus ions from dispersion medium. If FeCl3 is added to the excess of hot water, a positively charged sole of hydrated ferric oxide is formed due to adsorption of Fe3 plus ions. However, when ferric chloride is added to NaOH solution, a negatively charged sole is obtained with the adsorption of OH minus ions. Having acquired a positive or negative charge by selective adsorption on the surface of a colloidal particle, as stated above, this layer attracts counter ions from the medium, forming a second layer, as shown below. The combination of the two layers of opposite charges around the colloidal particle is called Helmholtz electrical double layer. According to modern views, the first layer of ion is firmly held and is termed fixed layer, while the second layer is mobile, which is termed diffused layer. Figure 5.3 depicts the formation of a double layer. Since separation of charge is a seat of potential, the charges of opposite signs on the fixed and diffuse parts of the double layer results in a difference in potential between these layers in same manner as potential difference is developed in a capacitor. This potential difference between the fixed layer and the diffuse layer of opposite charges is called electrokinetic potential or zeta potential. If two particles of an insoluble material precipitate do not have double layers, they can come close enough and attractive van der Waals forces pull them together. When particles possess double layer, as shown in figure 5.13, the overall effect is that particles repel each other at large distances of separation. This repulsion prevents their close approach. They remain dispersed and colloid is stabilized. The addition of more electrolytes to sole suppresses the diffused double layer and reduces the zeta potential. This decreases the electrostatic repulsion between particles to a large extent and colloid precipitates. That is why colloid is particularly sensitive to oppositely charged ions. Electrophoresis. The existence of charge on a colloidal particle is confirmed by electrophoresis experiment. When electric potential is applied across two platinum electrodes dipping in a colloidal solution, the colloidal particles move towards one or the other electrode. The movement of colloidal particles under an applied electric potential is called electrophoresis. Positively charged particles move towards the cathode, while negatively charged particles move towards the anode. This can be demonstrated by the following experimental setup. When electrophoresis, that is, movement of particles, is prevented by suitable means, it is observed that the dispersion medium begins to move in an electric field. This phenomenon is termed as electroosmosis. Seventh, coagulation or precipitation. The stability of the lyophobic source is due to the presence of charge on colloidal particles. If somehow the charge is removed, the particles will come nearer to each other to form aggregates or coagulate and settle down under the force of gravity. The process of settling of colloidal particle is called coagulation or precipitation of the soul. The coagulation of the lyophobic soles can be carried out in the following ways. First, by electrophoresis, the colloidal particles move towards oppositely charged electrodes, get discharged, and precipitated. Second, by mixing two oppositely charged soles. Oppositely charged soles, when mixed in almost equal proportion, neutralize their charges and get partially or completely precipitated. Mixing of hydrated ferric oxide, positive sole, and arsenious sulfide, negative sole, bring them in the precipitated forms. This type of coagulation is called mutual coagulation. Third, by boiling. When a soil is boiled, the adsorbed layer is disturbed due to increased collisions with the molecules of dispersion medium. This reduces the charge on the particles and ultimately leads to settling down in the form of precipitate. Fourth, by persistent dialysis. On prolonged dialysis, traces of the electrolyte present in the soul are removed almost completely and the colloids become unstable and ultimately coagulate. Fifth, by addition of electrolytes. When excess of an electrolyte is added, the colloidal particles are precipitated. The reason is that colloids interact with ions carrying charge opposite to that present on themselves. This causes neutralization, leading to their coagulation. The ion responsible for neutralization of charge on the particles is called the coagulating ion. A negative ion causes the precipitation of positively charged soul and vice versa. It has been observed that generally the greater the valency of a flocculating ion added, the greater is its power to cause precipitation. This is known as Hartley-Skulls rule. In the coagulation of a negative soul, the flocculating power is in the order aluminium 3 plus greater than barium 2 plus and then sodium plus. Similarly, in the coagulation of a positive soul, the flocculating power is in the order of FeCN6, the whole 4 minus is greater than PO4 3 minus, then SO4 2 minus and Cl minus. As the negative charge is higher, it has more power. The minimum concentration of an electrolyte in millimoles per liter required to cause precipitation of a sol in 2 hours is called coagulating value. The smaller the quantity needed, the higher will be the coagulating power of an ion. Coagulation of lyophilic sols. There are two factors which are responsible for the stability of lyophilic sols. These factors are the charge and solvation of the colloidal particles. When these two factors are removed, a lyophilic sol can be coagulated. This is done by adding an electrolyte and second by adding a suitable solvent. When solvents such as alcohol and acetone are added to hydrophilic sols, the dehydration of dispersed phase occurs. Under this condition, a small quantity of electrolyte can bring about coagulation. Protection of colloids. Lyophilic sols are more stable than lyophobic sols. This is due to the fact that lyophilic colloids are extensively solvated. That is, colloidal particles are covered by a sheath of the liquid in which they are dispersed. Lyophilic colloids have a unique property of protecting lyophobic colloids. When a lyophilic sol is added to the lyophobic sol, the lyophilic particles form a layer around lyophobic particles and thus protect the latter form from electrolytes. Lyophilic colloids used for this purpose are called protective colloids. Emulsions. These are liquid colloidal systems, that is the dispersion of finely divided droplets in another liquid. If a mixture of two immiscible or partially miscible liquid is shaken, a coarse dispersion of one liquid in the other is obtained, which is called emulsion. Generally, one of the two liquids is water. There are two types of emulsion. One, oil dispersed in water, OW type, and water dispersed in oil, WO type. In the first system, water acts as dispersion medium. Examples of this type of emulsions are milk and vanishing cream. In milk, liquid fat is dispersed in water. In the second system, oil acts as a dispersion medium. Common examples of this type are butter and cream. Emulsions of oil in water are unstable, and sometimes they separate into two layers on standing. For stabilization of an emulsion, a third component called emulsifying agent is usually added. The emulsifying agent forms an interfacial film between suspended particles and the medium. The principal emulsifying agents for O/W emulsions are proteins, gums, natural and synthetic soaps. And for WO, heavy metals, salts of fatty acids, long chain alcohols, lamp black, etc. Emulsions can be diluted with any amount of the dispersion medium. On the other hand, the dispersed liquid, when mixed, forms a separate layer. The droplets in emulsions are often negatively charged and can be precipitated by the electrolytes. They also show Brownian movement and Tyndall effect. Emulsions can be broken into constituent liquids by heating, freezing, centrifuging, etc. Colloids around us. Most of the substances we come across in our daily life are colloids. The meals we eat, the clothes we wear, the wooden furniture we use, the houses we live in, the newspapers we read are largely composed of colloids. Following are the interesting and noteworthy examples of colloids. First, blue color of the sky. Dust particles along with water suspended in air scatter blue light which reaches our eyes and the sky looks blue to us. Second, fog, mist and rain. When a large mass of air containing dust particles is cooled below its dew point, the moisture from the air condenses on the surfaces of these particles, forming fine droplets. These droplets, being colloidal in nature, continue to float in air in the form of mist or fog. Clouds are aerosols having small droplets of water suspended in air. On account of condensation in the upper atmosphere, the colloidal droplets of water grow bigger and bigger in size till they come down in the form of rain. Sometimes the rainfall occurs when two oppositely charged clouds meet. It is possible to cause artificial rain by throwing electrified sand or spraying a soil carrying charge opposite to one on the clouds from an aeroplane. Third, food articles. Milk, butter, halwa, ice creams, fruit juices, etc. are all colloids in one form or the other. Fourth, blood. It is a colloidal solution of an albuminoid substance. The styptic action of alum and ferric chloride solution is due to coagulation of blood, forming a clot which stops further bleeding. Fifth, soils. Fertile soils are colloidal in nature, in which humus act as a protective colloid. On account of colloidal nature, soils absorb moisture and nourishing material. Sixth, formation of delta. River water is a colloidal solution of clay. Seawater contains a number of electrolytes. When river meets the seawater, the electrolytes present in a seawater coagulate the colloidal solution of clay, resulting in its deposition with formation of delta. Application of colloids. Colloids are widely used in industry. Following are some examples. First, electrical precipitation of smoke. Smoke is a colloidal solution of solid particles such as carbon, arsenic compounds, dust, etc. In air, the smoke, before it comes out from the chimney, is led through a chamber containing plates having a charge opposite to that carried by smoke particles. The particles, on coming in contact with these plates, lose their charge and get precipitated. The particles thus settle down on the floor of the chamber. The precipitator is called corporal precipitate. Second, purification of drinking water. The water obtained from natural resources often contains suspended impurities. Alum is added to such water to coagulate the suspended impurities and make them
water fit for drinking purposes. Third, medicines. Most of the medicines are colloidal in nature. For example, argerol is a silver sole used as an eye lotion. Colloidal antimony is used in curing kala azar. Colloidal gold is used for intramuscular injection. Milk of magnesia and emulsion is used for stomach disorders. Colloidal medicines are more effective because they have large surface area and are therefore easily assimilated. Fourth, tanning. Animal hides are colloidal in nature. When a hide which has positively charged particles is soaked in tannin which contains negatively charged colloidal particles, mutual coagulation takes place. This results in the hardening of leather. This process is termed as tanning. Chromium salts are used in place of tannin. Fifth, cleansing action of soaps and detergents. This has already been described in the section 5.4.3. Sixth, photographic plates and films. Photographic plates or films are prepared by coating an emulsion of light sensitive silver bromide in gelatin over glass plates or celluloid films. Seventh, rubber industry. Latex is a colloidal solution of rubber particles which are negatively charged. Rubber is obtained by coagulation of latex. Eighth, industrial products, paints, inks, synthetic plastics, rubber, graphite, lubricants, cements, etc. are colloidal solutions. Summary. Adsorption is the phenomenon of attracting and retaining the molecules of a substance on the surface of a solid, resulting into a higher concentration on the surface than in the bulk. The substance adsorbed is known as adsorbate, and the substance on which adsorption takes place is called adsorbent. In physisorption, adsorbate is held to the adsorbent by weak van der Waals forces, and in chemisorption, adsorbate is held to the adsorbent by strong chemical bond. Almost all solids adsorb gases. The extent of adsorption of a gas on a solid depends upon nature of gas, nature of solid, surface area of the solid, pressure of gas, and the temperature of gas. The relationship between the extent of adsorption x by m and the pressure of the gas at constant temperature is known as adsorption isotherm. A catalyst is a substance which enhances the rate of a chemical reaction without itself getting used up in the reaction. The phenomenon using catalyst is known as catalysis. In homogeneous catalysis, the catalyst is in the same phase as are the reactants, and in heterogeneous catalysis, the catalyst is in a different phase from that of the reactants. Colloidal solutions are intermediate between true solutions and suspensions. The size of the colloidal particles range from 1 to 1000 nanometer. A colloidal system consists of two phases, the dispersed phase and the dispersion medium. Colloidal systems are classified in three ways, depending upon first, physical states of the dispersed phase and dispersion medium. Second, nature of interaction between the dispersed phase and the dispersion medium. And third, nature of particles of dispersed phase. The colloidal systems show interesting optical, mechanical, and electrical properties. The process of changing the colloidal particles in a sole into the insoluble precipitate by addition of some suitable electrolytes is known as coagulation. Emulsions are colloidal systems in which both dispersed phase and dispersion mediums are liquid. These can be of first oil and water type and second water and oil type. The process of making emulsion is known as emulsification. To stabilize an emulsion, an emulsifying agent or emulsifier is added. Soap and detergents are most frequently used as emulsifiers. Colloids find several applications in industry as well as in daily life. So here we complete the chapter surface chemistry. I hope you enjoyed listening to the audio. So please hit the like button, subscribe to the channel, and thank you so much for watching. Keep studying. Bye bye.